Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Welcome to Graphs of Functions. For the constant function, this is not going to be our main focus here, but I just want to remind everyone the constant function literally stays unchanging. So this would be like f of x equals, and then they might say 5. So it's non-changing, it never goes up, never goes down. This has a degree of 0. Once we move past that, that's what we're going to be more focused on today. So you might have heard the term linear before. Linear meaning line. Okay? Assuming that you have a positive slope, and we're going to assume for all these that there is we're going to assume just that a is greater than 0 for everything else. A would be our lead coefficient. Okay, so, and I'll talk more about that in a few minutes, what the a value is. But you'll notice that the slope was positive, and that's kind of what I'm saying with the lead coefficient is like, in this case, it would be the slope. Our slope is positive, meaning that the right side is up. Now in linear, we normally see y equals mx plus b. I'm going to call this ax plus b, since I used an a here. And we'll notice that the highest exponent is 1, meaning our degree is 1. And that it doesn't curve, there's no turning points. So the number of turns in this graph is 0. And that the max number of x-intercepts also happens to be 1. We might also notice that this is down. Another popular vocab word you've heard me use if you've watched some of these videos is quadratic. And I know when I talk to my Algebra 2 students, I talk about it being a smiley face. So in this case, we see that not only is it up on the right, it is also up on the left. And this would be y equals ax squared plus bx plus c. So in this case, the degree is going to be 2 because the highest exponent is 2. And it has that one turn. And I should say max number of turns. And the max intercepts in this case, it could cross the x-axis up to twice. Why twice? Because the degree is 2. That really does relate. It doesn't have to cross the x-axis. That's why I say the max numbers of intercepts. Okay, so our next one that we're going to draw up here is we're going to do an example of cubic. This would be a degree of 3. And I'm going to draw it as curvy as it could get. Okay, so the max turns is 2, and the max x-intercepts, I should have written x here as well, is 3. So you'll notice again the max intercepts matches the degree, because if the x-axis were here, it would cross 3 times. If it were down here once, if it came right across, it would get a cross and a bounce. So it's possible to touch twice, and we'll notice that it was down on the left and up on the right. And quartic is the last one I'm going to do. And we'll kind of get a W-ish kind of thing going. So quartic would be degree 4. The max number of turns, in this case we can see there's 3. And the max x-intercepts, if the x-axis were right here, it would cross up to 4 times. And again, it is up on the right. In fact, all 4 of them are up on the right. So the way that we can summarize this is when a is greater than 0, as x approaches infinity, y approaches infinity. In other words, the right side points up. The degree equals the max number of intercepts. One other thing you notice, what do you notice between the turns and the degree? 1, 0, 2, 1, 3, 2, 4, 3. Yeah. The max turns equals the degree minus 1. Now, what do you notice about the left side of the graph? Here, the degree was odd, and they pointed opposites. Here, the degree was even, and they pointed the same. Okay. Even degree. Okay. When x approaches negative infinity, y still went up. The left side was up. Okay, for an odd degree, the left side went down, right? So as x went left, y went down. If you have trouble writing your end behaviors using that direction approach, there's the odd degree, right? Here's the even, okay? This ends in quadrant 1. Quadrant 1 is positive, comma, positive. Hence why as x goes to positive infinity, y goes to positive infinity. See how the signs match the signs? Here, this is left and up. And that's why you're seeing what I wrote right here. This arrow is pointing into the first quadrant, which is positive, positive. This is in the third quadrant, which is negative, negative. Hence why that's what I wrote here. So you can use the signs of the ordered pairs to be able to help you figure out what you were to write. This pattern works for any y equals a x to the n polynomial. Now it can have pluses and things like that. This is considered a power function, and our domain is going to be negative infinity to infinity because there's no division by variables and there's no radicals. Our range, we're going to have to check out the graph to be able to identify, but our domain is going to be all reals. So those are power functions. When your f of x equals a times x to the 1 over n, that's no longer a power function. That's now a fractional exponent. Okay, this is the same as a times the nth root. of x. Okay. And again, if a is less than 0, it just flips the graph upside down. We've talked about how HK shifts in some of my other videos, how a just flips it upside down. So in case you've forgotten that, a, if it's negative, just reflects everything. What was up becomes down, what was down becomes up. Okay? If n is odd, your domain is all reals. For example, the third root, the fifth root, the seventh root, we can do that. If n is even, what's underneath the radical has to be greater than or equal to 0. Okay, so make sure you understand the difference between that. Of identifying when your domain is limited, again, it's only square roots of real numbers. This is not called a power function now, this is a root function. So the rules that we were talking about before was when n is an integer, okay? So power functions are when this is basically a whole number. 1, 2, 3, 4, 5. When you have it as a fraction, that's when things change. Okay, so let's say you were tasked with graphing f of x equals x cubed minus 8, x squared. Okay, it's cubic. We know that it has a positive lead number out, so we know we have probably 2 turns. We could have fewer. We should be able to see our arrows, and we should be able to see where this hits and where this hits. So y equals, clear this out, x to the third power minus 8x squared. And graph. Oh, okay, so I'm seeing like the peak, but I'm not seeing the valley. And I don't really need to go any wider. I'm wider. I just need to go down further. So in my window, I need to drop my y values. So now I'm going to go to negative 50. And since I'm going from negative 50 to 20, I'm going to number by tens because I don't want to number by ones. If I have to make that by hand, I'm not numbering by ones. Okay, that's better, still not quite there. So somewhere between 0 and, let's see, somewhere between 0 and 8, it hits the bottom. So I'm going to come into my table of values. And I notice here, if I pop over to my y's, it goes down at least as far as negative 75. So I'm going to come back into my window, and I'm going to go down to negative 100. And there I can see my key values. I can see that it's down on the left, it's up on the right. I can see where it hits a high point or a maximum and a low point or a minimum. And now I can actually translate this to the graph. Keep in mind that we numbered by 10, so this is 10, 20, 30, 40, 50, 60, 70, right? Well, we still numbered by ones on our x-axis. So as long as you're able to see all the key features we would expect to see, then we can definitely go ahead and look at this. So let's graph the following, and more importantly, let's worry about what the domain, the range, what am I going to want to see in my calculator. We're going to kind of pull back one of my previous videos on piecewise functions and combine it with this fact that we have these shapes going on. So x squared, 2x plus 1, 16 minus x is greater than or equal to 5. 1 is less than to x is less than 5. X is less than or equal to 1. So this is a piecewise function. So the first shape is a parabola because it's x squared. The end behaviors are going to match. Positive a value, it's linear. Now they wrote it backwards, but it's a negative a value, but it's still linear. So I should be seeing a parabola and an uphill line and a downhill line. Again, if you remember me talking in that previous video about how to type it, we've got to make sure we use all of our notations. And I always, always, always underline it in my graphing calculator just so I can see my end points. So we need x squared. Then there's that division sign. And the parenthesis, we need x. We go into our test window, which is that math button, third one down, it's right below the green one. And we need less than or equal to 1. Then we have 2x plus 1. And if you remember in my previous video, I said you have to type this in as two separate ones. So divided by 1 test. Now remember, I'm going to use menu number 6, not menu number 5, because I like it underlined. And then x, I forgot my parenthesis, divided by a second time and repeat. And then our bottom one is 16 minus x divided by x, parenthesis x, and that's number 4. Okay, so we have it typed in. I'm going to go ahead and go to my table first. So my parabola looks like it ends at 1, 1, and the y values here aren't completely unreasonable. The red one looks like it has a low y value of 3, and see how the blue one is going to stop at 1 and then we're going to pick up at 3, so there's some kind of gap going on. And then we're going to use the red until we get to 11, and then it's not going to have a gap till 11. So my x values I can see right here are staying between 1 and 5. So I'm just going to come back into my window. I'm going to go from -10 to 10 because that's my favorite x window. But my y's, it looked like I only needed to go up to 11, and I didn't see any negatives on there. So in my window, I'm going to go from -10, and then I'm just going to go up to 15. I could have went up to 11, but I don't like it hitting the top. And I'm going to number by ones. I don't mind that. I'm going to hit a graph. So there's that parabola, and then that gap. Okay, so that's what we would put on our paper. Now, be careful that your parabola is going to end at 1, 1, and that's going to be a close point. Right? And then we're going to jump to our red one, which is 1, 3. And that's an open circle, even though it told us where it was. And then it's going to go to blue, doesn't have anything. You don't expect it to. I need to know red is at 5, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 5, 11. And that was supposed to be an open circle, but the black one filled it in. And then we just need something else, because after we have that line, the other one's going to continue on infinitely. So if I just pick 6, I need it on the black line. There we go, 6, 10. And then we're going to put our arrow on there. So when you see me arrow, what I do, if it's on black and I need the blue, I arrow up. We'll see how I arrowed up and it went to the red. The red is not defined there, and the blue is not defined there. Only the black has an answer at 6. So that's important as well to note. But we can definitely use this to help us with our graphing. There is a strange kind of function that you might come into during this time. You actually kind of use it a lot, even, I mean, you use it just naturally. We adjust it from what this is. So it looks like this weird like double bar thing. And it's basically, it's a rounding function. This is known as the greatest integer function. And I like to think of it as the gravity or floor function. So you're in a building. Let's find f of 1.2. Okay, well, we're substituting 1.2 into this floor function thing. So if you're in an elevator or you're jumping and while you're in the air, your feet are at the 1.2 floor. Well, that means you're above the first floor but below the second floor, so gravity is going to suck you down to the first floor. Okay, so let's just do some other x values. What about 3.7? Well, you're between 3 and 4, but gravity is going to suck you down to the third floor. It didn't matter that we were closer to 4. Gravity is going to cause you to drop back down. You can put your pen almost on the ceiling. If you drop it, it's still going to fall to the floor. Now, if you're on the first floor, you're on the fourth floor. But what if you're at negative 2.5? Where's that going to fall? Now let's think about this. Here's 0. 1, 2, 3. You're right there. Which floor are you going to fall to? Yeah, you're going to fall to the negative 3. You're going to fall to the third floor down below ground. So basically it means what is the greatest integer you can come up with without going over? So get as close to negative 2.5 without going over negative 3. So our calculator can do this. In your math window, if you hit the math button and you arrow over to number, it's that menu number 5, int. So if we utilized 1.2, it was 1, right? So math arrow over number 5. Our next one was 3.7, right? Whoops, not 3 times negative 7. That changes it. There we go. Now I can type it in correctly. And math negative 2.5. There's that negative 3. So what does this look like when it's graphed? Well, first of all, to make it draw the graph correctly, if you go into your format, you should have asymptote detection turned on. Okay, that way asymptotes don't really exist. So if we come in here, and we're just going to graph the greatest integer x. So math, arrow over, number 5, x. And I'm going to reset my window to negative 5, just so that we can see key features better. It looks like a floating staircase. So instead of being linear, and going up 1 over 1, up 1 over 1, up 1 over 1. It's still doing that, but all the decimals got rounded to a flat. So instead of 1.1, 1.2, 1.3, 1.4, they got rounded down. The same thing, rounded down. All these decimals rounded down to 2, decimals rounded down to 3. It is a closed dot on the left and an open dot on the right. Without reformatting, it draws it faster with asymptote detection turned off, but now it doesn't look like a floating staircase. So remember, the graph is going to go open circle, open circle, okay. The computer, let me go ahead and draw my x-axis in here, just does this. And it puts in, it's like it draws a graph without lifting its pencil. That's what happens when an asymptote detection is turned off. So our domain is all reals. I'm just doing this verbally. But our range is just the integers. And so this time, this is one of those cases where we're using words as a better way to explain our range. And money is one of those times, like we don't spend $4.83.5. It's either going to be 83 cents or 84 cents. So money is an example of when you use a greatest integer or the floor function. I know a lot of places round up instead of rounding down. That's considered a ceiling function. So again, it's just a special function that kind of goes along with what we kind of do. Now, these are not continuous. And we do see step functions. We used to see them in our cell phone bills. So now we see them sometimes in our wireless bills. So let's say you get data for $25 a month for the first 100 megabytes. And then $20 for each additional 100. Okay, so what you're going to notice here is that, again, this isn't continuous because you're going to be at, let's say we go 10, 20, 30, 40, right? We number by tens. Well, we're going to be at $25 up until 100 megabytes. Once we hit anywhere after 100, we're going to have to add an extra 20 bucks. So now we're going to be at $45, right? So 30, 40, 50, 60. So here it'd be 45. And we're going to stay there for an extra until we hit 200 megabytes. After 200 megabytes, I should draw this better. Now we're going to add another $20. So continuous means you can do the graph without picking up your pencil. Here we can't do the graph because we are here. We're never going to pay $32.29. No, you're either going to pay $20 or $45 or $65 or $85, right? So step functions are not continuous because you have to lift up your pencil to go from one step to the next. So just understanding that what a step function is a great thing that we need to know. Again, this domain here, we wouldn't use negative megabytes. You're not going to give money back to them. So our megabytes, our domain, would be the number of megabytes used. And it would be 0 to infinity. And our range would be 25, 45, 65, ... And that one would just have to be written as a list, unless you wanted to create an equation. So step functions are definitely utilized in the real world.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.